All right, looks like we're back in business. Okay. So, well, partially. Anyway, so how does this work? How does it, let's see, somehow gotta get this to work. I might have to close and reopen this to get it to respond. Okay. All right. Get rid of this. Okay. Here we go. All right. So how does it work without the explicit invocation of this wrapper method? And that's where the fact comes in that the wrapper is an implicit method. So it says here implicit, and it is imported into this scope. You see, so when I say import scala mu to mu ops, it brings this implicit declaration into the current scope, and these occurrences of expressions of this type mu f, where f is x per f, these are expressions to which this implicit method applies. And that's how when you try to invoke a method in this result type, it'll actually apply this implicit conversion. So that way you basically get these implicit type conversions. And I think, well, obviously, if you get rid of it, these don't work anymore. But even if you put it, okay, it does work if you have it even in the outer scope. So I thought for some reason that didn't work earlier, but so looks like that's fine as well. So you could have it outside or inside, but in general, if you have trouble getting your code to see some other stuff, then try to bring the import closer. But, as we just saw, that shouldn't be necessary. So it should be okay for these imports even to live out here, and everything should be fine. Okay. Let's see. Okay. Yeah, so, in general, I would say it's a good practice not to import these kinds of implicits too globally. So it's probably just a good idea to have these things right here, for example. Okay. All right. So now the next thing is back to the structure. Because I think the behaviors are straightforward, right? The behaviors, we'll get to that in a second, but I think these are straightforward. But the structure has this other tricky part, okay? But anyway, so there's the straightforward part of the structure, which is your basically your variants of the common abstraction, the kinds of nodes you can have. So you introduce the common abstraction as a sealed trait, and then you state what kinds of concrete nodes that implement this common abstractions there can be. And that's the difference, right? So the non-leaves, the interior nodes here, plus and below, all have exactly 2 children, and so those are like composite nodes. And the U minus, one above, is like a decorator node. That one has exactly one child. And constant is the only kind of leaf we have here. Okay? So that is the difference. And this is now the crucial piece where you got to nail the functor. Okay. So, first of all, why do we need this functor? Well, the only one thing that the Scala mu framework or library, really, it's not intrusive enough to call it a framework. You know, it's a little library. So the one thing that mu requires indirectly is for this type argument f, of which mu forms this recursive fixed point at the type level, meaning converting x per f to an x per. That's mu's job, or shape f to a shape, forming this least fixed point. You know, so making a type that's not recursive, that has that still open argument a, making that into a recursive one by kind of plugging it itself into that slot for a. You know, that's how the kind of the recursive knot gets tied, and that's why we took a look at making recursion explicit at the value level. You know, how we made in the factorial the recursive call, you know, we disconnected it from the function itself, so it called another argument g, right? So the role of f here, the role of the a, okay, so the role of that a, the argument type of x per f, that's like the g in the prefactorial. It's basically that slot into which you can tie this recursive knot, and then you have the recursion. So this is at the type level, and what we saw last time is at the function or value level. Okay. So what allows mu to work, well, what are the prerequisites? Well, the direct one is the f we're converting into a recursive type, meaning least fixed point. You know, that means we introduce recursion. Has to have one type argument, meaning it has to be a type constructor of arity 1, okay? And we know a lot of examples of that: option, list, tree, set, you know, plenty of examples out there. Sequence, okay, stream, all of those are possible examples of type constructors that could be used as concrete arguments for this formal type argument f. So the difference between this f and the a is this a is a leaf type, meaning something like string or int or list of string, you know, something that doesn't want another argument before it's an actual type that has instances, right? So list as opposed to list of string or list of int, right? List wants that item type still. So that's why list just by itself is a type constructor, whereas list of string, you know, you can create an instance of that just by creating a list and putting some string values in it, okay? So this a is like int or list of string or string itself, or map from int to string, you know, something concrete, a type that you can instantiate. Well, I shouldn't say concrete, you know, but basically a type as opposed to a type constructor. So a type that doesn't want additional arguments before it can become a type. Okay? So whereas the f here has to be something that still wants exactly one type argument. And that's what this 1 underscore here says. So the a has 0 underscores. This f has one underscore, and there could be other type constructors of higher arity or higher kind that take multiple type arguments. Those would be represented as underscores separated by commas. So what's a good example I just gave of a type constructor of arity 2 that wants two type arguments? No, those are functions that want two values. We're talking at the type level. Map, exactly. Several of you said this. Exactly. Map wants the key type and the value type. That's exactly right. So that gives you an idea. So list just wants the item type. Map needs the key type and the value type. Yeah, in a way, yeah, it's related to that as well, because you could have, if you have a tuple of size 2, you need to say what the type of the first item is, and you need to say what the type of the second item is. That's right. That's probably one of the simplest possible type constructors that need multiple type arguments. That's right. But we need one that takes exactly one. So we cannot plug map in as f, but we can plug list in or option or our shape f or my expr f. Those are things that work here. But there's indirectly one other requirement, but they all satisfy this. They happen to satisfy it. So the co-free is basically a more general implementation of the mu. And Scala Z has co-free, so I just said, okay, well, let's just plug into that, instead of rewriting something like that, something slightly more specific from scratch. Okay, that's why you see the co-free here. And you don't need to worry about it. You will see when you print these things, a co-free at every node. That's kind of what you get when you form the recursion. So it doesn't really play any role other than being this wrapper that allows the recursion to be there. It basically means that when you wrap it, it's still the same as the children. Okay, and the second type argument in the co-free, unlike our mu, has, so each co-free node has a slot to put a value, and we're not using that, so that's why we're just plugging unit in. We're not using that here, so you don't need to worry about that. So this is really just an implementation concern. Okay. All right. So what is indirectly the requirement that co-free places on f? It says, well, for it to accept your f must be a functor. That's right. And that's why in several places, for example, for the kata, well, in the kata it doesn't show up. Well, it shows up kind of indirectly here. So meaning for all of these, whatever f we use, it should be a functor. So in other words, instead of the requirement for f to be a functor to be at the method level, that requirement is common to these methods. Otherwise, you could see that as some kind of implicit argument to the method or so. Okay, you see, like this one here, there is an implicit argument that says f should be a functor. So by the time you try to use these methods, that kicks in. That's why you're not seeing it explicitly here. That's why you don't see here that f should be a functor. So maybe one could actually add that. In what maybe one could say here, one could put that requirement here. So f : functor. I'm going to try that. Yes. Yes, that's exactly the next step, because now we're going to look at that. And so we need some kind of implicit, so I'll get to it in a second. So allow me just to finish this thought here. So for the mu to work on our x per f or equivalent, shape f, option list or whatever, that type constructor has to be a functor, and that means we have to somehow indicate this to the various other pieces of our puzzle that have that expectation, okay? And that's why we need something like an implicit declaration of our type constructor as a functor. So that's why we're saying this here. So we're, by creating this implicit object, we're saying, okay, from now on, or wherever you see this implicit object, wherever you're importing this, you will know, this is your witness or your proof that x per f can be used as a functor. Okay. So now, what is a functor? So a functor, you've already used functors a lot. Functor is extremely simple, but extremely useful. Often the simplest abstractions, the most general abstractions, give you the greatest utility. So what is a functor? A functor is a type constructor of arity 1, meaning a type constructor that takes one type argument, such as option or list or x per f or shape f, that has a map method which satisfies a couple of very simple laws. So that's a functor, and I will tell you what the laws are. The laws are the Functor Laws. We'll get to those momentarily. But there has to be, above all, a map method that you can apply on the functor. And the map method needs to have this signature. Okay. The map needs to work like this. If you give it an instance of the functor with item type A, and you give it a function from A to B, okay, then you get a functor of item type B, or you get that type constructor of item type B. And how is the original object and the result, how are the original object and the result related? Well, you take the original object, and everywhere in the structure where there is an occurrence of an item of type A, you apply the function f, and you get out the exact same structure, but all of the original items in the corresponding places are replaced by f applied to the original item. Does that make sense? So you've seen this a gazillion times. So for example, list map length gives you list 3, 2. There's your example. So the functor here is list. It has a map method that you're very familiar with. This is a particular f, which goes from string to int. Okay. So you get something that has the exact same structure, same number of items, but more than just the same number of items. The exact same skeletal structure. So the map method preserves that skeletal structure, but everywhere there is an item, it applies f, and in the resulting structure, it's f applied to the original item in place of the original item in the original structure. Okay? So if you have, let's see, if you have a tree structure, let's say you have a tree of strings, what will the result look like if you have a tree of these strings and you apply the length method? So this is obviously a tree of string, just like here we have a list of string. There we have a list of int. So here we'll also expect to get a list of int, and it's the same idea. Okay. So in a way, our expr_f functor, or a functor candidate, because we still have to look at the laws briefly, but in a way our expr_f and our shape_f are more complex in the number of branches that they have, okay? But they're simpler in what sense? What are expr_f and shape_f lacking that list and tree have, but option also lacks? So option, expr_f, and shape_f lack this characteristic, but list and tree have the characteristic. That's right. That's exactly right. So just the expr_f, you cannot build any structure other than one of these nodes. And you say, okay, well, there's that thing for A, so if I have an expr_f of int, I can have a plus with a 2 and a 3 in it, maybe, as the sub-objects, right? Just like option, I can have none or I can have some 7, okay? Whereas with list, I can have arbitrarily long lists. So list is a recursive type, and tree, of course, is also a recursive type. Okay, that's right. So that's an aside. But getting back to the functor property, so how does this map method work? How does it come into existence? Well, whoever implemented the list type implemented map, right? Or you could, in theory, inject it later using an implicit, as we saw. But presumably, when you're conceiving list, you know that you want it to be supportive of map. So that's just say more generally, you're thinking of it as a functor. But how does map work? How is it defined? Well, there are several ways to define map. One is to define it from scratch, right? You define it as a ordinary recursive method, and we've seen those examples. So we'll pull this up. MISC explorations. All right, so there are our functions on lists. So just like the reverse, we'll do a map. It's just a two-liner, just like reverse, right? So map would look like this. Okay, nil maps to nil. There's no item to apply F to. And if we have a non-empty list, we have the head and the tail. Well, we'll apply F to the head, and then we'll map F into the tail. And we're done, right? There's your map. Or you could implement map as a fold. So the fold is, the kata is the generalized fold, by the way. That's kind of the source of this power here. But yeah, so the map is very easy to write for list, even easier to write for option. But it's a little harder to write for our functor, not because of the presence or absence of recursion, but really because we have all these branches. Okay, so that's why our map needs an entry for each possible branch of our type, our type constructor. Okay, so this is the type constructor, and this makes the type constructor a functor. You know, this tells it, well, I want it to be a functor, and I'm giving you this map method. So that means now it's a valid functor from a typing point of view, because we're saying, well, we're saying it's basically an instance at the type level of this functor, what they call type class, and here's the required map method. Okay, so the map method, what we need to do is somehow to each possible kind of node, we need to say how we apply f to that node. So I just gave you the example for list. You know, for option, if you have some x, mapping that will be some f of x, right? So the u minus is like our sum in the option. Now, these are a little different in the sense that there's a fixed number of children, and that's that tricky part that some of you have already discovered, and it ties to what David was saying, okay? Without maybe intending to say it, you know, but you were saying, well, you were giving a tuple as an example. So a tuple has let's say a tuple of a particular size has a fixed number of pieces. You know, list has a variable number of the same kind of things. Tuple has a fixed number of possibly different things. You know, but let's say, what if we're looking at a tuple where both pair, a two tuple pair, where both pieces are of the same type. You know, so that's similar to what we have here, except we're not saying that it's a tuple, because we would need another pair of parentheses to express that, but that would be equivalent. We could do that. But so the thing is, what we're really doing here, even though it doesn't look like that, we want to apply f to each child of the node of plus. Yep.
I just have a question. So in the plus case, L is not necessarily, or is it an A type? Because it can be like another plus, can it?
No, it cannot. We have no recursion here at this point. There's no recursion until we introduce it explicitly using mu. That's a good question. You know, so right now, that's what makes this so incredibly simple. It's just like when you're looking at option of element type A, and you're looking at some x, there's nothing x could be other than an A. In particular, okay, well, so the answer to your question really does become yes and no. So in the following sense. It can only be a plus. So L can only be a plus if A is x per f of something else. So then what you're looking at is x per f of A. So until the point where you're introducing the recursion, you know, it kind of, these wrappers pile up. But when you do the recursion, when you introduce mu of x per f, that's this idea of the least fixed point, then you can pile up the structure, but it's still just an x per. That's exactly the key step here, you know, and that's why the recursion, this idea of the least fixed point plays this role. You know, so I don't expect us to understand this mathematically, you know, but at least I'd like us to have this working intuition that as long as we just have x per f, there is no magic here. So if we have, for example, you know, a sum of 3, it's an option of int. And here, if we have a plus of int, or like a u minus of 7, that would be an x per f of int. And the only way to get rid of this piling up of the wrapped type constructors is to tie this recursive knot So that means, well, as long as we're wrapping it in that thing, that's tied to the cofree or the in wraps it, and then it becomes an instance of the recursive version of that type. That's the thing that helps us, so that we can then build arbitrarily complex structures, and no matter how complex, it's still an instance of mu of x per f, or mu of our functor, meaning the least fixed point. And then it flattens it out. Okay. But so back to the definition of map here. Okay. So yes, all of these things are just like there. So whatever A is, L is an A, R is an A. The exception is V. V is whatever is defined here in constant. V is always an int. V. So the thing that is wrapped inside a constant node, that's always an int. That doesn't depend on A. And that's why it's okay to say constant is an x per f of nothing, just like none is an option of nothing, which is some kind of a type that doesn't really have any values. Okay. Unlike unit, which has one value. Okay. So in a way, nothing is the least general type, kind of the opposite of any. So any is here, everything is an any or an any ref, and then nothing is here, so you could also think about it as the bottom of the type hierarchy. Okay. All right, so back to the mechanics here. So V is always an int, so we cannot necessarily apply or necessarily want to apply F to V. We could only if A happened to be int, but we have to give a definition that works for all A. So the V, the constants and these leaf nodes are invariant under map. They should not be affected by the map. So that's the case here. Everything else where you have some kind of slot for a child of type A, you have to apply F. Okay? And now the connection to group. So in group you have a sequence of children, and you express that as a var arg when you build it. But you want to, basically you want to make sure, let's say you have 0 or more, right? So you have shapes, and then you somehow have to, in certain cases you have to say, treat this as a sequence of shape, or of A, sequence of A, okay, sequence of A, as opposed to a single value as part of the var arg, meaning a sequence of A with length 1. You don't want that. That's when you get these kinds of type errors. Okay, so you have to use this and that other thing with the at to make it match up properly. But so what do we really want to do? So when we apply F to L and R in plus, it's like considering L and R as a tuple and mapping F into the tuple. Okay? Whereas here we have 0 or more children. What do we want to do with F with respect to F and these children? So we get the group's shape, and so suppose you're doing group here, group shapes. How do we get the F somehow applied to the shapes? What do we use?
We have to use recursion.
This is kind of a thing that will ultimately result in recursion, but right here it isn't recursion because the type is not recursive in the sense that, so group is a shape F of A, right? So it has these shapes. What is the type of each item of these shapes? Well, we got to be careful here. What's the type of L? That's right. And the type of R? Right. How is it related to group and shapes? L and R are the same as 0 or more shapes, except that we have exactly 2. That's the connection here. So what is the type of shapes? It's already here. So in particular, shape F, that's why there is no recursion here, right? So shape F, it doesn't come into the picture here yet, until later when we make it recursive, But right now, what is the type of each item of shapes? A. That's right. So shapes is a sequence of items of type A. And we have an F. The F can take an A and give us a B. How do we put the two together? What method do we need to use on this sequence of shapes of type A? The map, exactly. But it's not the map we're defining, and that's why it's not recursive. It's the map that exists on these things. It's this map. Okay? Does that make sense? So we just say, well, we have 0 or more children. They're a sequence or a list or something like that. We can use that type's map to apply F to each of these children. Okay? So they're children not in the recursive sense yet. So these are just children of type A. They're really items contained in the group node right now, but they're of type A. So as long as we can somehow apply F to each of them, we get the same structure, but where we have B's, items of type B. And here, I'm summarizing basically. So here we have L and R, two separate items here, and each of them we can apply F to, and we get a B corresponding to the original A. Here, it's in a way even simpler because we don't need to write these multiple explicit applications of F. Here we just say, well, what is shapes? Well, it's a sequence of items of type A. Oh, sequence, that already handles map. And we can just use that map method. So it's like the one for list. We apply that. So it would look like something like shapes.mapf. But then, you have to use these things or this thing, whatever. So make the basically control any type errors or type mismatches. It would say when it thinks it's a single item, but you think it's actually a sequence, you can use these things and it'll all square up. Does that make sense? Okay. So your question about what a functor is has almost been answered because there's this other aspect which is actually almost trivial. It's the Functors Laws. These are very intuitive, so it's almost pretentious to call them laws, but they make a lot of these things work properly because they apply uniformly as long as something is a functor. So let's see. So if F is a functor, okay, and let's see. S is an instance of F of item type A, then S map of this function is what? And this function, we know we can just call it identity. In fact, in Scala, it exists as identity. What comes out of this? We get the same S back, that's right. So meaning, if we map the identity method for A, so this is the identity for A. If we map the identity for A into the structure S, we get the same S back because that identity method gets applied to each value inside S and transforms into itself and keeps it in the same positions in the structure, so we get back S. Okay, so the way you could write this simply is, let's see, you could say, well, map for F applied to identity is the same as the identity for F. Or more precisely, map F applied to identity for A is the same as identity for F. All right, because so the map applied to the identity for A is equal to identity for F, regardless of A, really, because we chose an arbitrary A. So this is the functor identity law, and this one doesn't, this we would expect. That's kind of that expresses our understanding that the structure gets preserved. Okay, and the other law has to do with composing functions, and that's, so for example, here, this I think we've seen examples of. Okay. Map, right? So we map length to this tree, we get that one, and then let's map something like argument plus 2, we get 5, 4, and 3. Okay. Okay, interesting. So how else could we have gone there? You see, so here we're taking this and we're applying map length, we get that, and then we apply to the result map plus 2 and we get this. How could we have gotten there directly? We could have said compose length and plus 2, mathematical function composition. So we could do a single map, and we could say, I'm going to write this as a mathematical composition, where you go from right to left, right? So you say the plus 2 comes after, this is the function composition, the dot length. So this is function composition. Okay. So here we're forming a single function, which, for example, if you give it the string ABC, it'll pump it in here. It'll give us 3, and then the 3 goes in here, and out comes the 5. So this is right now just a. Okay, so this is called the Functor Composition Law. So to write this in, let's see, so Functor Composition Law. All right. So S map for the same kind of S we have here. F, and then map G, so mapping F onto it first, and then G, is the same as S map G after F. Remember, so this is right to left here, the function composition, right? So this is the Functor Composition Law. So now, in very practical terms, what does this give us? Okay, so, you know, these kinds of laws, what good do they do us other than having some kind of apparent, you know, mathematical value and allowing us to reason about our code? Yep.
Won't that allow you to like get away from that stack memory problem if you have to allocate the space for all the math?
Mm-hmm.
Sequentially, I guess, it would kind of be sequentially having to add more structure or tree.
Yeah, so here we would need maybe an intermediate result. And then we would apply G, or the map G to that result. Whereas here we could do it in one step. So in a way you could say this Functor Composition Law gives us, it justifies this optimization, where we get away with a single traversal of the structure. This tells us that instead of traversing the structure twice by first applying F and then applying G, we could compose G and F and then just traverse the functor once. So it helps us decide to do this optimization. It tells us that this optimization doesn't change the result, which we would expect. Otherwise, it would mess up our results, and we would not consider it to be a valid optimization. That's right. Okay, so any questions about defining the functor here for shape F? Yep.
It's a question, like, here we didn't, like, the map
Mm-hmm.
method gets called, or it is applied only once, even on a composite shape, right? It's not a recursive. There is no recursive.
Okay, so we're defining map for shape F. And when we look at the group case, we use the map for sequence to apply F to each item in shapes, meaning in the children of, and that's in the children of the group node, and that's the map method for sequence or list.
How is the map implemented in that sequence actually?
Oh, like we just discussed, you know, like the reverse, or you know, just from scratch, because you're defining, you know, list is either empty or head followed by tail. So that is the recursive definition of the type. And along with that goes a recursive definition of any function. So you can implement most functions on these kinds of structures using this structural recursion. But then we also recognized, right, that we could pull out the common recursive pattern, which is the fold. But then that's for these things the kata. So you know, how do we get list, basically? I think now I want to inject this insight. So we get our special purpose, you know, domain model in the form of these trees by using this non-recursive functor x per f or shapes f, right? And then we apply the mu, we get the fixed point, right? We have this fixed point which works once x per f is established as a functor, okay? And we're good to go. And we get the kata method for it automatically from that, okay? How does this relate to list, in theory, at least? What plays the role of x per f? What plays the role that x per f plays for x per in the case of list as kind of the equivalent of x per? as a recursive type, right? So expr is making expr f recursive. What do you need to make recursive using something like mu to get list? And you will have only two cases. In expr f we have 7 cases, but for the list, the 2 cases that we just described. Right, exactly. So it's option. Option plays the role of expr f. So an option has none and some, right? So the none maps to the empty list, and the sum maps to a non-empty list. So that's right. And then to get these ordinary generic trees, what you make recursive to get that is stream. So that's the way all of these things are connected. And again, what I'm hoping that we're developing gradually is kind of a working intuition for these things. And then if anybody's interested, then you can start looking more at the mathematical underpinnings. But you don't have to. It's sufficient to have kind of a working intuition. Okay, so this is just the factory. And then the behaviors, they all follow that same pattern. Again, so any more questions about the structure and the functor? Are we pretty much good on that? Yeah.
Well, what about the factory?
Oh, yeah. What about it? Any concerns about the factory?
What is in?
Yeah. In goes with the mu. So in takes, so in is the price you pay compared to 2a, right? So when you define a data structure recursively using the recursion, the type level recursion that the language gives you, as opposed to what we're doing in here, like these 2 separate steps, functor and then mu. The difference is now we pay you the price of having to wrap something of expr f using in, and then it becomes an expr. And then it becomes arbitrarily composable without the types, these wrapped types actually occurring. What I was saying earlier, right? So meaning that here, so it ties to Derek's question, right? Once you form this least fixed point, so expr defined as mu over expr f, then you can say, well, constant c is an expr f of some type A. Okay. Okay, we don't get far there, but let's say the u minus is also an expr f of some type A. What type A? Well, it depends. We choose whatever we put in here. Whatever R's type is, that's A. So if R is an expr, then the type of u minus is what? Let's use our little thing because it won't work well with constant. That's really just a fluke, and I understand that some of you were thrown off by that. But again, the tooling here. So the type system is very complex. The tooling is work in progress, and this is a false alarm, and it's evolving. And maybe in a few months, they might fix this. They're probably thinking about how to fix this. And if you look at the tooling for the other language that has a similar type system, which is Haskell, it's nowhere near as nice as IntelliJ IDEA. If anyone has tried, and I know Derek has, right? And you looked a little bit at the tooling, and there's this Lexa IDE, but it's much more rudimentary. It's all right, but it's not as, it doesn't give you the kind of user experience that IntelliJ IDEA gives you. And I don't think it gives you code completion or anything like that, right? It's much more rudimentary. So this is actually a challenging task to develop this kind of tooling where essentially as you're editing, it keeps an internal representation of your program, you know, so it's kind of analyzing, doing static analysis of your program to figure out which expression has, which sub-expression has which type and so on. So I'm glad it is at this point because the tooling that I used to use for Scala was nowhere near as nice as this. You know, so I'm okay with a few little false alarms here. So and the type hints work actually. So on a Mac, there's a separate shortcut on Windows and Linux, but here I can say Shift Control or Control Shift P, and it'll tell me. It's too small for some of you to read, but it'll tell me this is a U minus of expr. So expr is A here, all right? And U minus is really just a special case of, 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 special case of,